Well, hello everybody. So, welcome to the 17th lecture of on the adiabatic two-phase flow and flow boiling in microchannels. So, what we were discussing in the last class was I think as far as I remember, we had started discussing the results on void fraction and pressure drop. So, what I intend to do today is I will be continuing with my discussions on the experimental observed trends of void fraction as a function of phase superficial velocities and conduit diameter, as well as maybe I will be touching upon the effect of entry section just as I had done in the case of flow patterns, and then we go on discussing the pressure drop. Once I discuss the experimentally observed trends which have been observed, then we go for the simple analytical models or the theoretical analysis of two-phase flow specifically for microchannels. Now, if we go for the results, we find that initially what do we find? We find that maybe if we take a larger microchannel, say 530 micrometer, 250 micrometers, these results have been reported in literature. We find that for the larger microchannels, more or less the void fraction which have been determined by image analysis and photography, and they are conventionally represented either as alpha versus phase superficial velocity. It can be alpha as a function of your either water velocity with the air velocity as parameter, or in other words, another conventional way of expressing the variation of alpha with superficial velocity is to plot alpha as a function of volumetric quality. If you recall the nomenclature part which I had discussed in the introductory lecture, you will understand that beta is nothing but the inlet volumetric fraction. Naturally, it is the ratio of the flow rates of the two phases. If the two phases are gas liquid or vapor liquid, then they can be expressed in terms of the volumetric flow rate of the gas flow rate and the liquid flow rate. So, therefore, if we plot alpha versus beta, it gives us an idea regarding the slip between the phases, where the slip can be defined as the ratio of the two velocities. It shows that how fast the lighter phase is flowing with respect to the heavier phase. So, therefore, in this particular case we find the researchers, they have represented void fraction as a function of volumetric quality, and we find that more or less for the larger pipe dimensions alpha is close to beta, although there is a trend of over prediction for the case of the 530 micrometer channel. On the contrary, when we come to the 250 micrometer channel, we find that there is a trend of under prediction, but nevertheless for both the cases we find that there is a linear relationship between alpha and beta for both the cases, and the relationship which can be given of the form as alpha equals to k beta, where we find that this particular k, it is a function of conduit dimension, as is evident from these two graphs. In this case, I would also like to mention that such type of linear relationships have also been proposed for macro channels. It was first proposed by Armand, so they are known as a Armand type of correlation. They were proposed with the value of k being close to equal to 0.833, and in this particular case we find that more or less k equals to 0.833 is not a very bad correlation. It is a correlation of Ali has used it for microchannels, but a better prediction would have been 0.833 in this particular case, or 0.9 here, and maybe 0.8 in this case, and maybe 0.9 in this case. We also find one more trend. We find that the deviation from alpha from beta, it is more at higher void fractions, and if we recollect, then we find that under these conditions the flow is actually annular, and when it is annular, then maybe most of these data have been obtained from image analysis and photographic techniques. So, therefore, there is a high chance that at such high void fractions, since the liquid exists as an annular film, it is very difficult to estimate the thickness of the thin annular film in this microchannel, and therefore, this particular deviation has been attributed to inaccuracies inherent in the image analysis technique by the researchers who have experimented on this. Now, we find that if we go to much lower dimension of microchannels, we find that the trend has reversed completely. In this particular case, we find that alpha is nowhere near beta, and if you observe it closely, we observe that at low values of beta till about say beta equals to 0.8, more or less linear relationship can follow. This occurs in both the 96 micrometer as well as the 50 micrometer channel, but after around 0.8, we find in both the cases the relationship becomes strongly non-linear, and in fact, it becomes exponential till alpha approaches the homogeneous value at higher values of void fraction. Also, we observe that at higher values, alpha does not reach its natural limit of 1, rather more or less it is around 0.833 in both the cases. So, it was quite evident that the relationship, the Armand type relationship which has been used for the larger diameter pipes with different values of k, it is not very applicable for the small dimensions, and accordingly a correlation has been proposed for predicting alpha in this particular small dimensions. This correlation is applicable both for circular microchannels and also for square microchannels, and it basically shows that when beta is small, naturally the effect of the denominator becomes almost equal to 1, and as a result alpha can be said to be proportional to beta, although the proportionality is not linear, and at higher values of beta the denominator becomes important, as a result of which alpha predicts a different trend from linearity for higher values of beta. Of course, several researchers have tried to work on to find out suitable values of C1 and C2, and it was noted that C1, although it is a weak function of diameter, C2 was found to be constant by one group of researchers. Again, there was another group of researchers who had suggested some different values of C1, where it was found that both C1 and C2, they are a function of hydraulic diameter. Since this is also evident from experimental results, we believe that the correlations proposed by Xiong gives a better representation of experimental data. Now, at this juncture, I would like to remind you that it is not very important that you memorize these particular correlations, at least for doing the assignments or the examinations which will be held at the end of the class. On the contrary, it is more important that you remember the form of the relation and also understand from physics why such a relationship has emanated, or in other words, why the alpha versus beta trend is different for your larger microchannels and smaller microchannels. So, we would emphasize more on the physics of flow rather than the mathematical form of the correlations. So, it's again I will repeat that for this particular class, you need not remember all the sets of correlations we will be giving to you. There will be quite a number of correlations in this class, since we will be dealing with pressure drop and void fraction, but it is again very important to remember why this correlation exists, why the trend of alpha versus beta is different for your larger microchannels and smaller microchannels, and so on. For example, in this particular case, if I ask you that why does the trend suddenly change around beta equals to 0.8, and why is the trend different for larger and smaller microchannels? So, in this particular case, if you observe closely, what do you notice? We notice that for smaller time, your lower values of beta, what happens more or less for your beta varying between 0 to 0.8. For this particular trend, what happens, you tell me? short liquid slugs and short gas plugs, they traverse in the microchannel, right. Now, whenever there are short gas slugs, because beta is low, so therefore, naturally as we increase or rather at lower values of beta, we have longer liquid slugs compared to gas slugs. So, therefore, if you observe the flow passage, you should be seeing short gas slugs followed by long liquid slugs and so on. Now, whenever we have this long liquid slugs, they increase the pressure gradient, and when they increase the pressure gradient, what happens? The shorter gas slugs, they tend to accelerate through the flow passage or through the liquid slug, and when they are accelerating, two things happen. Firstly, when they are accelerating, the residence time decreases, and when the residence time decreases, naturally alpha comes down. The other thing is from the measurement point of view, when the residence time decreases, they can very well evade they are captured by the image processing technique. Okay. They travel so fast that they can hardly be caught by the photographic technique. So, due to these two factors, very frequently we find that for beta ranging between 0 to 0.8, more or less, we find this particular trend where alpha it is much less than beta. Now, what happens when beta exceeds 0.8? We find under this condition, the gas slugs, they start becoming longer and longer, and they are often intercepted by short liquid slugs, which can be in the form of liquid rings, liquid lump, etc., or in other words, the liquid can just exist as a film and the gas slugs are long. Under such cases, what happens? There are two things, again the same thing. Firstly, as the gas slug increases, the pressure drop decreases. So, there is a lesser tendency of the gas plugs to accelerate and to travel very fast through the liquid slugs. Due to this, the residence time of the gas slugs decreases, and there is a greater probability of them being recorded by the camera. Firstly, secondly, as the gas slugs become smaller, their residence time increases, so naturally alpha also increases. So, this explains the nature of the curve which we find, and this explains why this particular correlation is suitable. Now, if we compare them with the larger microchannels, in larger microchannels what do we find? The gas liquid interface is much more wavy, it is much more deformed. As a result, the gas slugs exchange far greater momentum with the liquid, and due to this enhanced momentum transfer, it hampers the gas slugs from speeding through the liquid. So, naturally alpha is higher in larger microchannels as compared to lower microchannels. This has explained two things. One, the decrease of alpha with decrease in conduit dimension. The other is the non-linear nature in smaller microchannels. Well, just like for flow patterns, we had discussed that there is a distinct effect of entry section. We had also like to see the effect of entry section in this particular case as well. Now, what people have observed, again it has been reported in literature by just one or two particular researchers, and not much work has happened on this, and these researchers, they have also commented that the effect of entry section, although it has received very less attention, this is definitely a very critical parameter for deciding the flow morphology and the hydrodynamic characteristics. Now, what is the effect that has been observed? It has been observed that usually we know that the flow in this particular case can be broadly classified either as quasi homogeneous, which is alternated by short gas and liquid slugs, which happens at low values of alpha, or it is quasi separated, where it is alternating flow of long gas core and thin annular fill, and maybe there is a long liquid slug which moves very, very slowly. It has been observed that usually a T junction inlet, it gives rise to the quasi homogeneous flow, while a reducer inlet gives rise to the quasi separated flow. Again, more important than memorizing this particular fact is why might this at all happen, because once you understand the logic, it will be easier for you to remember and appreciate the fact. In this case, it was observed that naturally when there is a T junction, what we find is that the two phases, they are flowing from diametrically opposite points, then the liquid naturally it has got a pinching effect on the gas, the liquid, due to its natural tendency of wetting, it wets the pipe wall, it falls something of this sort, and the gas, it has to pierce through this liquid core and then start falling. And the shearing effect of the liquid velocity, it breaks the gas slugs into smaller gas plugs, and this gives rise to the so called quasi homogeneous flow, or it gives rise to the normal plug flow which we observe. And when we have a reducer inlet, what happens? When we put a reducer, both the phases, they tend to get accelerated, and but naturally the gas slug, it tends to get accelerated more. So, therefore, there is a greater tendency of the gas slugs to come closer to one another and to coalesce to form long gas coats somewhat similar to the annular flow pattern, and therefore, it marks the transition between the slug and the annular flow pattern, and this explains why a reducer inlet gives rise to the quasi separated flow. On the other hand, a T junction might also give rise to a quasi separated flow, provided the T junction inlet is about 2 to 3 times greater as compared to the microchannel diameter. Why? Because in this case, the pinching effect is counteracted by the reducer effect, and as a result, the reducer effect becomes more prominent. It can also occur when the T junction inlet has the same diameter as the microchannel inlet, provided the inlet gas volume is so large that it can form, or it can give rise to some compressible gas effect. Moment that compressibility comes into factor, the gas slug, it tries to accelerate and expand and accelerate at under a significant pressure gradient, and naturally it gives rise to a quasi separated flow. Now, with this we have already discussed the effect of entry section, the effect of conduit diameter, the effect of phase superficial velocities denoted as volumetric quality on the void fraction for adiabatic gas liquid cases. Now, what happens for heated tubes? Now, as I have told you that for adiabatic cases, usually photographic is the more commonly used techniques, the other techniques are not so very much used, and lot of the counterintuitive phenomena which we observed were attributed to the errors involved in the measurement of very thin films or fast moving slugs, etc. Now, for heated tubes, usually how do we measure the void fraction? It is almost the same the way we measure the flow patterns. Photography is definitely one technique. Now, for void fraction, there is also an indirect way of measuring void fraction. How is it? If you remember the way we had defined what is void fraction, basically this is nothing but equal to the inlet gas velocity denoted as the volumetric flux divided by the in situ gas velocity. This is termed as the inlet gas velocity, which can very well be defined by the volumetric flow rate divided by the conduit cross sectional area, and this is the in situ gas velocity, which is naturally the volumetric flow rate divided by the cross sectional area, or at the AG, the cross sectional area which the gas occupies when it is flowing along with the liquid in the conduit, right. Now, suppose we have an independent measurement of QG as well as UG, then we can find out alpha from these measurements. Measuring QG is not at all a problem. We know the conduit dimension, we can measure the inlet volumetric flow rate by any particular conventional flow measuring device, and we can find out JG. What about UG? Now, one particular method of finding out UG is by computerized image analysis of high speed, high definition video camera sequences. This we have discussed a large number of times. Other than that, there can also be a method which is based on conservation of mass. This is particularly applicable for the plug flow pattern, which is much more prevalent in microchannel boiling two phase flow. In this case, the velocity of the elongated bubble in a microchannel can be derived as a function of bubble length and conduit diameter by defining a parameter gamma. What is this gamma? This gamma, it is the gradient of the superficial bubble velocity along the channel axis. So, therefore, what we do, we define gamma as the gradient of superficial bubble velocity along the channel as axis, assuming two things. One is there is no liquid or vapor which is evaporating, and the annular film surrounding the bubble is very thin compared to the microchannel diameter. On the basis of these two assumptions, the expression of gamma reduces in terms of the uniform heat flux applied to the evaporating fluid, the latent heat of vaporization and the density of the gas. Now, once gamma is known and the length of the Taylor bubble, it can be estimated from photography, then UG can be decided, the velocity of the Taylor bubble relative to the homogeneous flow velocity can be expressed by this particular expression. We would remember CO is the confinement number by which we had defined microchannels while we were discussing what defines a microchannel in one of my earlier discussions. Now, from here we find out UG, and once we find out UG, then definitely we can use this UG here and we can find out JG. Now, several people, this Revlin and Thome, they have tried this out and they have found from the expression the two things. The alpha, it is a function of length, and longer the bubbles, greater is the deviation of alpha from alpha h. Now, this is what we had observed in our experimental results, even in the case of your adiabatic cases as well as in previous experiments performed in boiling heat transfers. We find that in this particular case we have shorter gas lengths and shorter liquid flux, and it is more of slug flow, and under this case alpha was close to alpha h. One particular reason of the deviation of alpha from the homogeneous value was the change of flow patterns and the elongation of the gas slugs. This is also brought about by the expression which has been derived from mass balance. And it implies that as during heating or during boiling, as the two phase mixture proceeds along the channel due to evaporation, the bubble, it grows in length, and as a result of which alpha keeps on changing. We find that the increase of the velocity with respect to bubble length, initially it is much more rapid and then it becomes much more gradual. So, therefore, there was one way of finding out UG by photography, there was another way from the mass balance equation, and the third way, if you remember when we were discussing the experimental estimation of flow patterns, we had discussed an optical probe technique. By this optical probe technique, I had mentioned that we can know the distribution of the voids, which gives us an idea regarding the flow pattern. Now, suppose we have two optical probes at a known distance from one another, and in these two optical probes, if we note the signal, then we find that for both the probes, suppose we plot voltage versus time, for plug flow we get a signal something of this sort, and for the other probe which is located at a little distance away, we get a signal something of this sort. Now, if we cross correlate the signals, then from the location of the valleys, from this particular time intervals, we can find out the time of travel of the plug, and knowing the distance between the two probes, we can find out the Taylor bubble velocity, and since the entire gas flows as just gas plugs in this small channels, so they only give us the dimension of UG, and once we know UG from here and we can measure JG, we can find out alpha once more. Now, in this particular case, there is just one thing which has to be kept in mind, the distance between the two optical probes, because if the distance is such that it is much larger than the length of individual plugs, then it will be very difficult to capture the plugs. So, therefore, the spacing, it should be optimum such that it can note the velocities for bubbly slug or slug flow patterns. If you would wish to use it for bubbly pattern, the two probes should be brought closer to one another. This has to be considered. So, this was for a heated tube. This is the technique by which we can do it. Now, we come to pressure drop measurements. Now, in the pressure drop measurements, what we find is that most of the data in the mini channels, and not much has been done, but whatever has been reported, they are primarily for the mini channels, and there is scarcity of experimental data as well as predictive model in micro channels. So, therefore, naturally some amount of results have been reported, but there is good amount of controversy, and we find that there is quite a number of limitations of measuring pressure drop in micro channels. The first thing is that it is quite obvious that the pressure drop in this case is primarily frictional, isn't it? So, therefore, and the conventional technique of measuring pressure drop is to connect the tappings to the inlet plenum and the outlet plenum and measuring the pressure drop between these two, because it is very difficult for making pressure tappings at the intermediate positions. The thing which we do for larger channels, we have two pressure tappings in the region which we consider as the fully developed flow, and then we measure the pressure drop there, but that is not possible for the case of micro channels, and this is the conventional thing which is usually done. Now, when this particular technique is developed, then we find that there are quite a number of limitations and uncertainties associated with the pressure drop measurement in this particular case. So, in the next class, we will be discussing the uncertainties associated with the pressure drop measurements. We will be discussing some typical pressure drop results for oil water and the air water flows, and then we will be shifting to the analysis of two phase flow in micro channels. Thank you very much.